overview of sort of methods for causal inference. I think if I have time, I'll have a couple slides at the end talking about new topics in that area and with some references. And again, John, I shared the slides with John, so these should be available to you all, hopefully, in some way, shape, or form. John, is there an easy way to sort of get it to people?
Yeah, so after the talk, I think we'll share it on the WNAR website. So,
Awesome.
yeah,
Great.
thank you.
All right, thanks. Okay, so I guess we can't really talk about medical research without talking about the medical uh, topic of our time right now, which is COVID-19. So I just want to start off with a quick topical example, which is actually a study that just came out this year in the New England Journal of Medicine looking at the real world effectiveness of the COVID vaccine. And again, by real world effectiveness, what I mean here is basically that people sort of in Israel they had a vaccination program. They had pretty high rates of vaccination, and they basically want to see, based on sort of vaccinating people, how did that how effective was the vaccine, sort of in a setting that was not a randomized clinical trial. And again, sort of causal inference, just more generally, is going to be talking quite a bit about how you try to attempt to come up with inferences that are in the spirit of those you'd make from randomized clinical trials when you have data that is non-randomized. So let me zoom in here a little bit. So with this, you can basically see that what they did in this data set, if you look at methods, is they use matching to basically sort of start to mimic the clinical trial design, and they sort of matched people who had gotten the vaccine to people who hadn't, based on a variety of what they call demographic clinical characteristics. And basically they found, even in this setting, kind of what we've seen in the vaccine trials, that while the vaccine is kind of effective in sort of preventing transmission of getting COVID initially, it's very effective from all the bad things that happen from COVID. And again, they sort of basically replicated a lot of the vaccine trial findings with their analysis in this paper. So today, my goal are to basically talk a little bit about causal inference and sort of talk about the framework. Let's see. Okay. Okay. Thanks for the suggestion, Anna. So we'll be talking about sort of causal inference, and then so here are the goals for today. So to start off, it sort of just to sort of give you a bit of a cultural bent here. So what causal inference does at a very high level is basically ask the question of how a person-specific outcome changes under different scenarios. And I'm a big movie fan. There are actually examples of people doing sort of causal inference types of things in movies. So one is this famous scene from The Matrix with Keanu Reeves, where he's Neo, he meets Morpheus, and basically Morpheus offers him two pills, the red pill and the blue pill. So basically, imagining Keanu Reeves taking each of the pills would be the potential outcomes. Another movie, which sort of has a counterfactual sort of setup as well, is the movie Sliding Doors, which came out, I think, in the 90s with Gwyneth Paltrow. There, the counterfactual is she arrives at a train. She arrives at a train, and in the two counterfactuals, in one scenario she gets onto the train, in the second one she doesn't. So, two good movies I recommend, and indirectly a way to learn about causal inference.
Debashis, sorry to interrupt. I think we can't see your slides now.
Yeah, sorry. Uh, Thanks.
Oh, there we go.
Okay. The good news is, yeah, this is the non-mathy slide of the talk. So, okay. Thanks, John. So again, with causal inference, the fundamental notion here is counterfactuals. This is also called the potential, also referred to as potential outcomes. So I'll basically have one running example throughout the talk today. So it's given here. So this is a paper that came out in JAMA Internal Medicine 2017. Um, so the question that the investigators asked in this paper was, is exposure to a statin in the early perioperative period associated with reduced post-operative complications after non-cardiac surgery? So what we're going to basically look at is the use of statin the day of or day after surgery and its effect on 30-day mortality. So one thing I'll say during this talk is I'll sort of be asking lots of questions, which I'll let you sort of think about during the talk. So one question here would basically be, how do you actually think about estimating this effect? So in this database, they basically had an observational database. So this is a database on patients who had undergone non-cardiac surgery. This was taken from the VA, the Veterans Administration Surgical Quality Improvement Program. And basically what they wanted, so this was a database where basically they had patients that sort of had been given statins or not given statins during their surgery period. And what the investigators wanted to do was basically see, can you come up with a measure of effectiveness of the statin? So in this paper, which we'll talk about a fair bit throughout the talk as our running example, they used propensity scores to model the treatment effect. And then they sort of did matching to sort of get to a randomized type of design. So this is going to be the recipe for causal inference we'll be talking about in the talk today. So it's basically a 6-step kind of process. So one is to obviously figure out what your exposure is. The second one will be defining the causal parameter of interest. The third is modeling the treatment or assignment mechanism using propensity scores. And then in step 4, we estimate the causal effect conditioning on the propensity score in some way. We're statisticians, so an effect size isn't enough for us. We also want a variance of that estimated effect size, so that'll be step 5. And then step 6, I'll talk about sort of thinking about the big issue with these models, which is that there's unobserved confounding and how you might think about doing sensitivity analyses. So on to step 2. So let's go back to why be the outcomes in those movies. So from the matrix, one causal effect is that what happens to Neo when he takes the blue pill, what happens to Neo when he takes the red pill, and looking at and comparing the difference. In Sliding Doors, Helen, the protagonist played by Gwyneth Paltrow, her catching the subway and her not catching the subway, and what happens. Those are the two potential outcomes, and looking at what changes. And the question is, why are these causal effects? They're causal effects because what causal inference tries to do is basically compare potential outcomes within the same person. So on the previous slide, it was the fact that we were comparing Y for Neo only within Neo, or Y for Helen only within Helen, is what made it a causal effect. So if you want to do this, right, basically you're going to need to imagine or come up with a way of envisioning what Y would be for a given person under every scenario you want to consider. Now the problem is that when you collect data, you only observe data on Y under one scenario. So, and this is what gets referred to as the fundamental problem of causal inference. Okay, so I usually find sort of pictures a little bit helpful for thinking about how to model causal effects. So we're going to talk about a situation where basically a person has two possible treatments. Treatment t equals 1 or control t equals 0. So you can basically visualize data for doing causal effect estimation sort of with this table I have here. So I basically have a table with 3 columns and n rows. And basically what you see is, if we look at the first row, that person received the treatment. And for them, we observe their Y because they got the treatment. So that's little Y1. They were not a control, so we did not observe Y0 for that person. So basically, if you go through each of the rows, you basically see that for each row, we have one little y and one question mark. So a couple things to point out here, and we'll get to them later as well. One is we're actually making an implicit assumption that the y we observe is the same as the counterfactual or potential outcome y. And that gets referred to as a consistency assumption. The other thing to know is that basically we have a question mark. And if we want to have a hope of estimating causal effects, we need a way of sort of filling in the question marks. So basically what sort of happens here is that the question marks, it defines the missing data mechanism. And like I said, if we can fill in the question marks with y values, then we can basically look at differences within each row to get a causal effect. So again, the setup is that if we have a binary treatment that takes values 0 and 1, the vector y0, y1 is the potential outcomes for an individual. So basically, by definition, this is if we want to model this, we have to think about models for bivariate distributions. So some terminology, causality is typically tied to an action, which is also gets referred to in the literature as manipulation, treatment, or intervention. Based on what we then want to do is consider what are the list of possible actions. So in the example I've shown you so far, the action here, action space is, do they get the treatment? Do they not get the treatment? The action is applied to a unit. The unit here in that example I showed all of you, the unit is each row of the matrix or the table. And the presumption is that at any point in time, a unit could have been subject to either action. And then basically for each unit action pair, which is each entry in the y columns, we associate a potential outcome. So in a sense, I'm now showing you sort of the same kind of table as before, but now I'm showing you the table without question marks. So the full data for causal inference would be visualized in the way I've just shown you here. So if I had this, I'd sort of be done, because basically I'd just compare the numbers within each unit. And by unit, I mean within each row of the table to get the causal effect for each person. So treatments. There's actually a fair bit of controversy on how do you define treatments. And again, sort of the way I talked about it is you're sort of applying something to units. So sort of, I think things we care a lot about these days, thinking about sort of things like equity issues. Ideally, if we did this, we would like to sort of, ideally, we'd like to be able to say what's a causal effect of sort of race or of gender due to sort of the structural disparities we see with that. That being said, it's really not easy to, those typically don't get treated in this causal inference framework because sort of in this kind of maxim that Rubin and Holland talk about, you really can't talk about interventions without being talking about being able to manipulate the intervention. So you have to think really carefully about sort of what mechanisms you can imagine that would sort of are amenable or not amenable to manipulation. So what that also means is kind of like the way sort of with these structural equity issues like with race and gender, people have thought about it too is, there's potentially causal effects, but you might think about not just causal effects, but you might think about what they call causes of effects, which is a different thing I won't talk about today. So again, causal effects are by definition going to be comparisons of potential outcomes made within a unit. Typically when we fit regression models to data, we're typically talking about subpopulations defined by observed covariates. So in general, when you fit regression models to data, they typically don't enjoy a causal interpretation unless you make further assumptions, which we'll talk about later. So here's one example here, which is looking at systolic blood pressure. So I have one y variable, which is systolic blood pressure, and then I'm sort of dichotomizing age to being above or below 45. So the beta 1 would basically be saying what's the difference in systolic blood pressure for people above 45 versus people below 45. So beta 1 is a measure of association, but in general, beta 1 is not a causal effect unless we make more assumptions. And obviously we're talking about causation, but really, that phrase we always sort of say to people about correlation, not causation, is kind of key here. And I think sort of one thing I do want to sort of stress is correlation is easy, causation is harder. And I think in a way, I almost feel like a lot of what needs to be done when you think about doing causal effect estimation is even thinking about sort of thinking through mechanistically, like what could potentially happen to be generating the causal effect you care about, and whether the mechanism that you're sort of imagining sort of makes sort of has reasonable scientific or biological plausibility. So here's one example of a causal effect based on that full table I showed you guys a couple slides ago. This is basically taking the outcomes within each unit and taking their difference. So the causal effect is what's given on the rightmost column, y11 minus y10. So basically, each number here is a causal effect. It's a causal effect for the person or the unit in that row. So one way of comparing two numbers is to take the difference. Another one might be the ratio. So this is giving you the ratio. So this is yet another causal effect. So that was a causal difference on the previous slide. This would be a causal ratio. So what we're showing on the previous page were individual level causal effects. So one natural thing to do is to average the unit level causal effects across units. So one question I have for you is if we were to take the sum of the effects and average them across the rows, what assumption do we make when we do that? So I'll give you guys a few seconds if someone can answer in the chat box. Okay, so I will let you think about that throughout the talk. And if you have questions, we can come back to it at the end. So another way you can actually do this is you can actually define causal effects based on subgroups. The subgroups can be based on observed outcomes or even potential outcomes. So another question I have for you, which we can revisit at the end, is what assumption do we make when we do causal subgroups? So I mentioned assumptions that sort of you need to go from thinking about empirical correlations or associations to causal effects, and I've sort of listed them here. So we'll go through them a little bit here quickly. So they're called the strongly ignorable treatment assumption, stable unit treatment value assumption, treatment positivity assumption, and consistency assumption. So we'll start with the strongly ignorable treatment assumption. And here's sort of the mathematical definition I have in the equation, which is that y0, y1 are conditionally independent of t given x. T is the treatment, y's are the potential outcomes, and x are the confounders. So treatment is conditionally independent of the potential outcomes given the confounders. So in words, what this really means is that your X space is so rich that you can basically think of the potential outcomes as sort of determined at, or effectively determined at baseline. So again, it's a very sort of conception. And again, sort of if you go back to and we'll get to a picture here shortly, but you'll basically see that that with the X's, kind of the way they work is they're meant to be used to fill in the question marks that I've shown you before. And again, like I said, when you think about the question marks are defining a missing data mechanism. So another way of sort of just thinking about the strongly ignorable treatment assumption is equivalent to saying that the question mark, if strongly ignorable treatment assumption holds, it's equivalent to the question marks representing a missing at random mechanism. And if you're familiar with missing data, if you have missing data that are missing at random, what that means is you can use your covariates, your X, to fill in the missing values. So here's kind of visualization now that we're talking about. And so now I have expanded the table from before, where I now have added in X's, which are covariates. And again, I have P covariates, and again, I'm simplifying things here a lot by assuming that basically on the X's I have no missing data. So what the strongly ignorable treatment assumption says is I can use the X's to fill in the question marks. Once I fill in the question marks, I can then basically take comparisons of y1, y0 within each row to get causal effects. The next one is that stable unit treatment value assumption, or SUTVA. Again, I've sort of just given you the same matrix as before. Or table, and what SUTVA basically says is that the potential outcomes between the rows are independent. And again, you can imagine one place where this doesn't hold. Again, I mentioned the COVID example at the very beginning. COVID is an infectious disease. If I am infected, that is probably very likely to impact the COVID status of, for example, members of my family who live in the same house with me. So in infectious disease settings, you basically have a violation of this SUTVA assumption, because then if you have sort of family units or clusters, you can imagine that the potential outcome of one person impacts the potential outcome of another person through the infectious disease transmission. And again, sort of the violation of SUTVA is what gets called interference in the statistical literature, and there's lots of papers about that. I won't be talking about that any further today, but just for you to know about it. Treatment positivity. So this is saying that the probability of treatment, and again, we'll be assuming pretty much throughout that the treatment is binary, that it's sort of strictly between 0 and 1 for all subjects and for all x values. And this is basically needed to have sort of well-defined counterfactuals for defining cause effects. And again, a question that I'm happy to sort of address at the end is, when would this assumption be violated? So I mentioned consistency. So we formulate y0, y1 for everybody, but we only observe one of them. And consistency basically means that the potential outcome and the observed outcome are the same. So I would say sort of the 4 assumptions I mentioned, probably the one that sort of generates the least controversy is this one. If you don't assume this, what that basically says is that any of the data you've collected on y cannot really be used directly for cause effect estimation. Or another way, you'd almost need a model you'd basically not need to worry about the joint distribution of the y0, the y1, and then your observed outcome, which becomes 3-dimensional instead of 2-dimensional. So again, just as a recap here, there are a lot of assumptions that you need to sort of identify causal effects using observational data. And another big challenge is that most of these assumptions, they're not like residual analysis for linear regression. You can't really look at empirical checks of the data to test these assumptions. So let's go back to that paper. So I told you the treatment was basically exposure to statin on the day of or day after surgery. So if they did get statin, their treatment was a 1. If they didn't, it was a 0. And then the outcome was death within 30 days. And in this database, they had follow-up for at least 30 days on everybody. So basically, y was observed for everybody. So their causal parameter in this paper was basically the ratio y1 over y0. Okay, so come back to that recipe. The next is, how do we model the treatment assignment? And again, the main thing we'll be using here quite a bit is our propensity scores, which we'll go into next. So we've now talked about, we sort of conceptualized the data structure for causal inference problems. So now we'll talk about kind of what we observe. So yi obs is basically going to be the observed response for subject I. And this is basically a way you can link up the observed outcome, defined on the left, with the potential outcomes on the right. So basically you see that if t is 1, yi obs is the same as yi1. If t is 0, which means they're control, then you basically, yi obs is y0. Now, if t were a result of a coin flip, you basically get 50-50 chance of heads or tails. You get this probability mechanism. And the coin flip is basically what a clinical trial does. However, this is not true for what happens in an observational study. So what happens there is basically, because patients or subjects are self-selecting into treatment groups, this probability of treatment assignment isn't random. So basically the question then becomes, can we sort of model the coin? And just as a preview, what the propensity score really does is to basically model the coin flip. And it models the coin flip as a function of the confounders of the person. So again, an assignment mechanism, it refers to how each unit came to receive the treatment actually received. And the propensity score is one attempt at modeling that mechanism. It's defined with the equation given here. So E of x is basically the probability that you have treatment given the confounders. And again, this was sort of made famous in a paper in 1983 by Rosenbaum and Rubin. Conditional on this propensity score, one achieves covariate balance on observed covariates. So what's key here, though, we'll talk later about what covariate balance means. The balance that you get is only on the things that you measure. You're still not guaranteed. So what's powerful about a randomized clinical trial is that because of the coin flip, you're guaranteed balance in theory on the things you don't measure. You don't have that here without the further assumptions of without the propensity score plus the CETA assumption. So if you use propensity scores, if you want to start to do modeling, you basically estimate propensity score in step 1. You check for balance, which we'll talk about shortly, and adjust accordingly. So basically, if you don't have balance, you then have to figure out a way of making things look more balanced. And then based on the estimated propensity score, you estimate the average causal effect. So, what variables do you put into the propensity score model? So the recommendation initially by Rubin was to look at all possible treatment confounders and interactions on quadratic terms. One type of variable that Rubin sought to, that is sort of known not to be avoided is what's called instrumental variables. And instrumental variables are basically variables that might be predictive of the outcome, but if you condition on some intermediate variable, they're no longer predictive. And like I said earlier, the SITA assumption, kind of philosophically, what that sort of says is it sort of argues implicitly that you want to collect a lot of variables for that conditional independence to hold. The problem is if you include instrumental variables as part of your conditioning set X, you're going to get what gets referred to as collider bias. And what collider bias has is this effect of basically biasing your causal effect estimate in a way that you might not, in a way where you can't even predict the direction of the bias. So again, what you really want to be doing with a propensity score model is include as many variables in the propensity score model that you think will be strongly predictive of the potential outcomes. So again, you don't want to be strongly predictive of T, because if you're strongly predictive of T, you run the risk of violating that treatment positivity assumption. You might get probability treatments for people given their covariates that are close to 0 or 1. So you don't want that. So yes, you want, so it's very sort of non-intuitive. You want, even though you're modeling T given X, the X's you want are really those variables that will predict Y1, Y0. And again, we'll talk later about this, but you'll want to be checking for balance of the confounders after you fit this model. So here's sort of a thing I use for describing balance. This is a figure some of you have probably seen before in some of my talks. So this is a simple case of one confounder, X. I've simulated from a mixture of normals. So basically for the pink or magenta line, it's normal 0, 1. For the bluish purple line, it's normal mean 2, variance 1. And you basically see, so apply your histograms and density estimates for the confounder in the two groups. So again, if we sort of look at this picture, we basically see that the most amount of overlap between the two groups is actually in the middle. So if I use subjects in the middle of the distribution, i.e. where things overlap, that is where I have a chance of having robust causal effect estimation based on the subjects. If I go to the far left of the picture, here are people in the control group that have no one with comparable X values from the other group. If I go to the far right, I have people with X values in the treatment group that have nobody really comparable from the control group. So in the far tails of the distribution, I'm basically going to have only one group and not the other. So I'm not going to be able to really estimate causal effects very well in that part of the space. And again, if you think about a propensity score model, I want to predict probability of treatment, I'm going to have the hardest time predicting probabilities of treatment for people that are in the middle, because they have a chance of being either from the group T equals 1 or T equals 0. So in a way, just intuitively, the region of the covariate space where I have where I can estimate causal effects pretty well happens to be the region of the space where my propensity score model, which would be a one-dimensional model here, would actually not predict the treatment group very well. Because in the far left, I'm very certain that the predicted treatment will be control. In the far right, I'm very certain that the predicted treatment will be the treated group. Okay, so now thinking about balance, and this sort of comes from a paper by Liz Stewart in 2010, Statistical Science. I'm basically going to figure out so I have, again, a recipe here, just like I do for this overall 6-step recipe. So I'm going to decide on which covariates I want balance to be achieved on. Figure out how I'm going to estimate distance between people. Once I've, and again, a very common one people use is to look at propensity score distances between people. And I basically want that to be sort of small between treated and control people. And then I'm going to condition on the distance measure. And again, we'll talk about some of these methods later. You could use matching, weighting, or subclassification to do the conditioning. And then once you have that conditioning, you then want to basically check to see, am I being balanced on the covariates of interest? Again, I sort of need the balance to make sure that the reason I observe the causal effect I do is because of the exposure of interest, the T. I don't want there to be confounding. I don't want that effect to be confounded by other covariates. If my other covariates are imbalanced, there's a possibility that that imbalance it might be driving why I observe the treatment difference I observe. So I check for balance on the covariates of interest. If the balance is poor, I'm going to basically sort of repeat steps 2 through 4, so this becomes potentially an iterative process. When I'm happy with the balance I've achieved, I basically then estimate the treatment effect in the condition sample. I'll say here in passing that there's been a bunch of recent work in the last few years where basically people try to do causal effect estimation, where as part of the effect estimation, they impose balance directly. So in particular, there are methods such as the Covariate Balance Propensity Score and entropy balancing, where people are estimating causal effects, sort of using while simultaneously enforcing balance in the confounders. So that's sort of an interesting literature, which I'll allude to today, but I won't talk about any further unless people have questions at the end. So let's talk about covariate balance. So we have, again, our treatment, which is binary, and X are confounders. So what we want for balance to happen, we basically want that the joint distribution of X in the treated and the joint distribution of X in the controls, they look pretty similar in distribution. And again, if this holds in the original data set, that's actually kind of what you might expect to happen when you have a randomized study where you've randomized T. Again, typically in causal, so this would be sort of the kind of thing where if you are computing table ones for medical articles, table ones would basically, and you have a two-group comparison, table ones would basically be looking at the distribution of X and this way. The big difference there, though, is typically they do that on a marginal basis, looking at each variable at a time. So typical ways to assess balance, you can report standardized mean difference, use Kolmogorov-Smirnov statistics or t-tests. And again, covariate balance, and again, this is very sort of non-intuitive. So for covariate balance to be happening, it means that you have smaller standardized mean differences, smaller Kolmogorov-Smirnov statistics, smaller t statistics, or less significant p-values. But in a way, this again sort of runs very counter to how we do statistics, because it's almost like for balance to hold, what you need to do is prove the null hypothesis. And again, we can't prove the null hypothesis if we're using sort of classical statistical frameworks. So when this ends up sort of, and we'll see this in the example in the paper we've been talking about, they basically sort of had a sort of a heuristic rule of thumb for how you sort of check for balance that they applied. And we're there. So again, they basically did, and we'll talk about sort of the algorithms a little bit later. They use propensity score matching. So for each person, they calculated a propensity score based on their confounders. Again, they had the treatment, statin, within 7 days or not. So for each person that received statin, they tried to find someone with a similar propensity score that didn't receive statin, and they sort of did this by matching pairs of people. They also used what's called a greedy matching algorithm, which we'll talk about a little bit later. And to evaluate balance, they sort of also allowed for there to be a little bit of variation in the propensity score. So they used what's called a caliper width. So that sort of says that the propensity score here is going to be effectively a continuous variable given the number of confounders and the sample size. So it's going to be hard to get exact equality of two individuals having the same propensity score. So they basically use this caliper width to say, I'm going to get very, very close in propensity score for the two people. So once you had that, you had the match pairs. And then in the match pairs, they basically evaluated covariate balance. And they sort of use the standardized difference for these different types of variables. And basically, if the standardized difference was less than 0.1, they called it minimal imbalance. And in a way, I sort of like this. I like this phrasing of it, because they didn't conclude balance; they just said minimal imbalance. So, question in the chat here. Yeah, it's a great question, Katie. So this is sort of the nuanced part of it. The statistics they use correspond to statistics they use in hypothesis testing, but they're not trying to make any sort of decision. They're not. They use them in a qualitative way. So everything you said, again, I'll let everyone read in the chat. Everything is true. So I will say, sort of early on, there was sort of people that sort of would sort of use the p-value in the wrong way that you're describing, and sort of saying if the p-value was insignificant, they had balance. So nobody really does that now. Again, it's their descriptive measures they're using are kind of they correspond to the statistics in hypothesis testing, but I would say they sort of use them qualitatively. So okay, so next up, we want to estimate the causal effect, and so now we'll get to sort of some methods for causal effect estimation. So this is sort of I know it's too early in the morning to do statistical theory, but you can sort of show with that SITA assumption and treatment positivity that sort of using conditional iterated expectation that you have these equalities holding. So basically the key point here is this thing on the right is the expected value of a potential outcome for subject I. The thing on the left is basically the conditional expectation of something that we either observe, which we see in the numerator, or something we can estimate, which is the propensity score in the denominator. So basically, if I now take the difference of these two expected values, I get the average causal effect. And that's basically what you have in this picture here. In this equation here. So this is what's called an inverse weighted causal effect estimator for the average causal effect. And I mentioned earlier the extreme positivity, which says something like the probability has to be bounded away from 0 and 1. So you can imagine here, if I have an estimated propensity score, E hat of X, and the E hat is close to 0 or close to 1, this estimate's going to blow up. Because basically you're going to be dividing by 0 for one of these terms. So things that get done there are basically, one thing people do is they basically try to avoid having really, really extreme values of E hat, meaning they try to trim out values of E hat that are close to 0 or close to 1. So a fancier approach is combining inverse regression and inverse weighting with regression adjustment. And you might have heard of this as what's called double robust estimators. So I've basically given you the formula here. So basically, if you were to compare this to the previous slide, term 1 and term 3 are kind of the same. What's happening that's different here is you're basically sort of subtracting or adding in a new term. And that term is basically the treatment minus its expected value, which is the propensity score divided by that. And then you're sort of multiplying it by m1 hat of 0, m1, and m0 hat, m1 hat, m0 hat. So again, m1 hat and m0 hat are basically the estimated functions for the y's. So m1 is for y in the treated, m0 is for y in the control. And basically, again, it's probably too early in the morning for most of us to be doing delta method asymptotics, but basically you can use things like the delta method to find out the asymptotic variance, or in practice you could also use the bootstrap to get the variance. Okay, so these double robust estimators, they're very popular in statistical research. I think they're sort of, I would say, slowly diffusing into sort of practice. And again, these m hat values, so I gave you a sort of a complicated looking form, but basically they're sort of thinking about, they come from basically fitting a regression model of y on x and the two subgroups, 2, 0 and 2, 1, and then getting the fitted values. And then you can basically use those in those regression estimates. So they're basically, if you're using R, there's something you might get from a predict function. So predict applied to some regression model or an object. So the pros of the method is that the double robust estimator can be consistent if either the propensity score model or the outcome regression model is correctly specified. So basically, you have two chances to be right. If one of them are right, your estimator for the causal effect will be consistent. if they're both correct, your estimator is actually going to be sort of inefficient in a very sort of certain technical sense. The con obviously is now I have to fit two models. So if I get both models wrong, then the double robust estimator can actually perform pretty badly. And again, there's sort of a super nice paper from about 14 years ago by Kang and Schaefer in statistical science, where they sort of show, sort of using a fairly data-informed simulation model, that sort of double robust estimators, perform worse than sort of even simple non-fancy causal adjustments. So those are weighting estimators. Another approach that gets used a fair bit is matching, and I've shown you the example at the beginning with the vaccine efficacy in Israel, and obviously in this paper that we've been talking about by London et al. They use matching. So the idea here is based on the estimated propensity score for each subject with t equals 1, try to find one or more subjects with a similar propensity score from the control group and compare the responses. And the treated subject and the set of controls, we'll call that a match set for subject I. So this is basically the formula for the average causal effect when you do matching. And again, what you should notice here is basically I'm taking the so yi is basically the outcome for someone in the treated group, the ith person in the treated group. For them, I'm finding mi controls. And the controls have tj equals 0. I'm just comparing the y's. So in a way, right, if you're familiar at all with things like machine learning, in a way, this is kind of like a nearest neighbor kind of estimator, where I have a very special definition of neighbor, right? Basically, the neighbor are going to be the closest points from the other group based on propensity score. There's sort of an extension of matching, which is a little bit more robust, where you basically take the propensity score and you coarsen it, and it's called subclassification. Another approach, a way of adjusting for the propensity score, and I won't talk about that today. So in this paper, they created a matched paired data set using propensity scores. Once they did that, they estimated their causal effects using matched pair methods. So again, their outcome was binary. They had a binary exposure. They basically used conditional logistic regression to estimate the effect. So they use so one thing to note here is that basically their initial set size was almost 180,000 people. They reduced it down to 97,000, so they actually dropped 100,000 subjects. So one question that I think doesn't get asked enough is like they basically dropped their sample size by 100,000 to estimate this causal effect, and the question might be how systematically different are the excluded observations from the included observations, and that's something I've sort of been thinking about as sort of a important diagnostic to look at. Okay, so based on the exposure, we have an effect estimate, which statisticians, we want to get a variance for the estimated effect. So how do we get a variance? So think about variances. They're actually sort of, we need to do one sort of conceptual thing, which is think about what kind of inference we want to do. And people on the audience who are familiar with things like survey sampling are probably familiar with the concept of finite population sampling versus superpopulation sampling. So that's kind of the sort of the big divide here is how do you want to think about doing inference here? Do you want to think about it on a finite sample basis or on a superpopulation basis? So this is that picture I've shown you before. If we want to think about a finite sample, our population that we care about is fully represented in this data set. So a finite population would basically assume that like what we have effectively
Sorry, everyone. I think we're having some technical problems. So hopefully Debashis will get back on momentarily. It looks like he's lost connectivity. So just sit tight and we'll see if we can get him back.
Sorry, everybody. That's what happens when internet dies at work. I thought it'd actually be safer here than at home. Let me share screen first. So I will just sort of say, just for you guys, since you guys are still here, I think since my drop off was random, uh, and I think 5 or 6 people left, you could say that my getting kicked out of the Zoom meeting had a causal effect that was negative in terms of attendance. Um, okay, so let me back up here. So superpopulation sampling basically says that this is a finite sample. So if I want to do finite sample inference, I'm basically just going to think about the n people and their question mark distribution. So you can basically use the randomization distribution of t to do inference. So then you shuffle the label, and then you get estimated standard deviation conditional on propensity score by doing that. So you want to think about superpopulation, which is the alternative way. The idea now is that basically the observed units are a random sample from a bigger population. So in that example I've shown you guys, we have n people, and those n people were sampled randomly from some bigger population. Still me. Okay. Okay. So let me go back here. So this is a finite population. This is a census. We use randomization to get the distribution of the potential outcomes. The alternative is superpopulation. With superpopulation, uh, you assume that the n people come from some bigger population and they're randomly sampled. So now when I look at, so again, this is the finite sample estimator, looking at yi1 minus yi0 for the an average that over everybody. When you do the superpopulation, when you do expected value, you're gonna take the expected value with respect to the sampling mechanism and not with respect to t. So that's the big difference between the two. So again, there's lots of, in the book by Emmons and Rubin, there's lots of derivations about superpopulation inference. So key results are that the expected value, where the expected value is taken with respect to sampling, is given by, has this expected expectation. Here's the variance of the finite of that difference in the average causal effect and definitions here. So coming back to the paper, they created this match pair data set of roughly of 90,000 observations. The authors then estimated variances of the effect using match pair methods. So we talked about conditional list regression, and basically the models they were fitting were effectively random effects models. So they were basically allowing each match pair to have its own random effect. So again, the random effect models, because they're random effects, they're in spirit they're superpopulation, but their estimation was using conditional regression. So in a way, their estimation method was also finite sample. So it had a little bit of both. So it's kind of hard to classify exactly like what kind of inference they did. Finally, we want to get to talking about sensitivity analyses for unobserved confounding. So again, if unobserved confounding happens and CETA does, that SITA assumption doesn't hold. So the way we sort of do this is, even though we might assume that t is not independent of the potential outcomes given x, but that it is if I add in a u, So U is basically going to be a synthetic covariate, which is simulated under the control of the user. So you basically write down a model for y given x and u, and t given x and u. You can let the coefficient of u vary, and then you estimate everything across the two models. And if you sort of do that, you can sort of get a causal effect estimate as a function of u. It's hard to implement because it's going to be computation intensive. So one very nice simplification is due to Lin et al. In a biometrics paper from about 23 years ago. So the idea is you basically use what I call monomalous specification theory. So far we've been talking about your parameter estimates like average causal effect, and it's consistent. When you have consistency, we talk about theta hat converging probably to the true theta. So if the model isn't true, it's going to converge to something different, right? So it's going to converge to what's called the least false parameter, theta star. And it turns out theta star is going to minimize the Kullback-Leibler divergence, here's a Wikipedia reference on that. So basically, you think about violation of theta as one of fitting the incorrect model. So true model is y depends on t, x, and u. False model depends on t and x. And you basically get, and if you look at the paper by Lin et al., you basically get some very nice, simple approximate formulas for sensitivity analysis. So in this Lin et al. Paper, they did lots of data checks and dropping data and sort of those kinds of sensitivity analysis, but they actually didn't really do anything for the unmeasured confounding. So a question that gets asked is, with unmeasured confounding, the thought of unmeasured confounding is how big does your confounder need to be to basically reverse or change the effect size that you've observed? If the amount of confounding is small in some sense, that sort of suggests that your final observational study result might be fragile. If the final confounding has to be really, really big, unmeasured confounding, that sort of suggests that your finding is more robust. Because if your confounding effect needed to be really big to change the answer, that's probably a variable you have collected for in the analysis already. So in the interest of time, like I said, the two sort of hot topics, I'll just give a couple slides on them. So one is called transportability. And this is sort of also talks about how do you merge randomized clinical trial evidence with real world evidence. So the idea is to take effects from randomized studies and see how it carries forward to observational studies. So I've given you guys some key papers for looking at this. So I think sort of the first prominent example of this was done by Cole and Stewart in a 2010 American Journal of Epidemiology paper, where they basically had data from a randomized clinical trials in HIV, and they then sought to see could you transport that effect that they found to sort of an observational HIV database. Udea Pearls talked for a long time about graphical approaches to formulating causality and determining confounder criterion and identification of causal effects. So he has a paper with Elias Barenboim in PNAS in 2016 where they talk about transportability criteria and sort of data fusion. There's sort of a very nice discussion paper by Peters et al. In 2016 in Jarris's B where they talk about this idea of what they call prediction and variance. And it turns out prediction and variance are precisely the causal estimands that transport across studies. So again, in that paper, they sort of give you criteria and ways of estimating those effects. And then finally, there's been a lot of work out of the Boston area on sort of using transportability, and there's a really nice paper by Dehabre et al. In 2020 in Statistics in Medicine on that topic. Another topic that's pretty cutting edge is mediation analysis. So the idea is you have an exposure that affects a mediator that then affects the outcome. So the canonical approach to doing this is given by Barron and Kenny in 1986, and it's probably one of the highest cited papers I think in the literature. More recently, the question becomes they were thinking about a one-dimensional exposure, a one-dimensional mediator, and a one-dimensional outcome. So now we have lots of big data Can you see everything okay? Thanks. Thanks. So here's some papers. So basically, 1 and 3 are genomics mediators, which are high dimensional. The second one is fMRI, or brain imaging data as a mediator. So some really cool things going on there. So just to wrap up, what causal inference tries to do is basically, through assumptions and modeling, use observational data in a way that you can sort of mimic randomized studies. Propensity score model basically plays the role of a coin flip, or the randomization mechanism. So this is something to keep in mind. It's basically the Y model is the scientific outcome model, and the propensity score model is the coin flip model. They play different roles in the analysis. So one thing people have tried to do in the past, which was not the right thing to do, was basically think about the Y and the propensity score as a joint model and try to model things that way. But if you do that, you start making the assumption that the Y and the propensity score sort of play the same role in the analysis, and they really don't. We talked about a 6-step pipeline for analysis. And then there are lots of assumptions that are unverifiable, so sensitive analysis is important. And again, sort of transportability and high dimensional mediation. So with that, I'll wrap up. And as a reminder, I think John just double check. We will make these slides available to everybody, correct?
Yes, that's right. The slides will be available, and the recording of the talk will also be available. So I think thanks to Debashis, I think we maybe have time for 1 or 2 questions from the audience. So go ahead, post them in the chat, or sorry, go ahead.
Yes, no worries. I see one in the chat box, so maybe we should take that one. So this is a great question. In the after your talk, you mentioned generalizability and transportability. Could you explain whether there's a difference between the two? So the answer is yes. In the following way. So when we think about, I think what it boils down to is sort of the idea of your populations. And so when we think about transportability, we have a study population, and basically, so let's see. So how we think about a big population, we sort of and there's a big population we care about. We do a clinical trial on a subset of them, the ones that want to be in the clinical trial, and then we ask the question: is what we found in the clinical trial subset applicable to the entire population? That would have been the hypothetical you would have wanted at the beginning. Generalizability: we have one population that we estimate something on. We sample a new population and ask the question: does the effect that we saw in the initial population carry over to the new population? That's generalizability. So in a way, the sampling is kind of what's like. So the transportability assumes I have one big population and I subset it out. The generalizability assumes I have one sample, I estimate something, I get a new sample from this sort of superpopulation, and does that effect replicate? Okay. Question here from Katie. I talked about X confounders. Does a variable need to be the criteria to include among the X's? What affects the outcome? Yes. So variables that affect outcome. Yes. So that's exactly kind of what you do want. Are exactly those. A variable that affects outcome associated with treatment. You want that in your propensity score model. Yes. So again, really, what the confounders really do in this framework, right, is to basically really influence how you do the coin flip. And for a coin flip, what X's do you need to sort of influence that probability? But yeah, you would definitely want ones that include the outcome in the coin flip model.
Okay, thanks, Debashis. I think we're going to wrap up now, everybody. So again, let's thank Debashis for joining us today and speaking, and thank you all for coming. And as Debashis was saying, we will be posting the slides and the recording of the talk. So, thanks, everyone.
Thank you, everybody, for your time. Have a great weekend.
Bye.